Hello there, and welcome back to the Sleepy Science Society. I'm so glad you found your way here tonight. Maybe you've had a long day, or perhaps you're the kind of a person who likes falling asleep to cosmic wonders rather than counting sheep. Either way, you're in the right place. Before we begin our gentle journey through the stars, if you enjoy these explorations into the universe and find them helpful for unwinding at the end of your day, consider liking this video and subscribing to the channel. It helps others discover these calm conversations about the cosmos, one sleepy soul at a time. Tonight, we're going to explore our home in the universe. Not just Earth, not just our solar system, but the vast spiral of stars that contains them both. The Milky Way Galaxy, a colossal wheel of light turning slowly in the darkness, home to hundreds of billions of stars, and yet we've only begun to understand its secrets. We'll drift through its structure, explore its hidden masses, visit its violent core, and trace the paths of ancient stars that remember when our galaxy was young. We'll discover recent findings that have changed how we see our cosmic neighborhood, and we'll contemplate our place within this spinning disk of starlight. So settle in, let your breathing slow, and your thoughts drift. There's nowhere you need to be, nothing you need to do. Just rest here as we wander together through the grand architecture of our galactic home. The Milky Way's scale and structure. When you look up at the night sky on a clear, dark evening, away from the glow of cities, you might see a faint, hazy band of light stretching overhead. The ancient Greeks called it the Milky Circle, and that name has stayed with us through millennia. For most of human history, no one knew what this pale river of light truly was. Some cultures thought it was a path for spirits. Others imagined it as spilled milk from the breast of a goddess. It wasn't until Galileo pointed his primitive telescope at this band in the early 1600s that the truth began to emerge. That milky glow was not a cloud or mist, but countless individual stars, so distant and numerous that their combined light blurred into a continuous ribbon across the heavens. Today, we know that the Milky Way is a barred spiral galaxy, one of billions scattered throughout the observable universe. But being inside this structure makes it incredibly difficult to see its true form. Imagine trying to understand the layout of a vast city while standing in the middle of a crowded street. You can see the buildings around you, perhaps glimpse some structures in the distance, but the overall plan, the grand design, remains hidden. That's our situation with the Milky Way. We're embedded within its disk, surrounded by stars and gas and dust, trying to piece together a map of something we can never step outside to view. Nevertheless, centuries of careful observation, measurement, and increasingly sophisticated technology have revealed the Milky Way's basic architecture. Picture a grand spiral, somewhat like a cosmic pinwheel, but with a thick bar of stars cutting across its center. From this central bar, spiral arms sweep outward, trailing through space like the arms of a spinning dancer. The whole structure spans roughly 100,000 light-years from edge to edge. To put that in perspective, light traveling at nearly 300,000 kilometers per second would take 100,000 years to cross from one side of our galaxy to the other. The scale is almost incomprehensible. And yet, for all its breadth, the Milky Way is remarkably thin. The main disk, where most of the stars reside, is only about 1,000 light-years thick. If you were to scale the galaxy down to the size of a dinner plate, its thickness would be less than that of a sheet of paper. This flatness is the result of angular momentum. When the primordial cloud of gas that would become our galaxy began to collapse under its own gravity billions of years ago, it spun. As it contracted, conservation of angular momentum caused it to flatten into a disk, much like pizza dough spun by a chef spreads into a flat circle. But the Milky Way is not a simple, uniform disk. It has structure, layers, regions with distinct characteristics. At the very center lies the nucleus, an incredibly dense concentration of stars packed tightly around the supermassive black hole known as Sagittarius A. Surrounding this core is the central bulge, a somewhat peanut-shaped region roughly 10,000 light-years across, glowing with the light of billions of older stars. The bulge is not perfectly spherical, but rather has a three-dimensional shape that swells in the middle and narrows at the ends, like an hourglass or a cosmic peanut. This strange geometry likely formed from the galaxy's central bar, a dense stripe of stars that rotates slowly, buckling and puffing upward over billions of years. Then there's the disk itself, actually composed of two components. The thin disk, where our Sun resides, contains younger stars, open clusters, and most of the galaxy's star-forming regions. It's approximately 1,000 light-years thick and rich with gas and dust. Above and below this lies the thick disk, a puffier structure containing older stars with fewer heavy elements. Stars in the thick disk move on more tilted, elliptical orbits, suggesting they formed under different conditions, or were stirred by early galactic collisions. The disk is where the spiral arms are most prominent, those great sweeping arcs that trace out regions of enhanced star formation and glowing nebulae. Surrounding all of this is the galactic halo, a vast, nearly spherical region that extends far beyond the visible disk. The halo is populated sparsely with ancient stars, many of which are metal-poor, meaning they contain very few elements heavier than hydrogen and helium. These stars likely formed in the early universe before generations of supernova had enriched the cosmos with heavier elements. The halo also contains globular clusters, tight spherical collections of hundreds of thousands of old stars that orbit the galactic center like moths circling a distant flame. Some of these clusters are more than 12 billion years old, nearly as ancient as the universe itself. Recent measurements suggest the Milky Way contains between 100 and 400 billion stars, though the exact number remains uncertain. Our Sun is just one of these countless points of light. Located about 27,000 light-years from the galactic center, roughly 2/3 of the way out from the core to the edge. We orbit in a relatively quiet region called the Orion Spur, a minor arm nestled between two larger spiral structures, the Sagittarius arm and the Perseus arm. It's a fortunate location, far enough from the dense and dangerous inner regions, yet not so distant as to be in the sparse, metal-poor outer reaches where planetary systems might be harder to form. The entire galaxy is in constant motion. It rotates, but not like a solid wheel. stars closer to the center orbit faster than those farther out, though this difference in speed creates the spiral arm patterns we observe. Our solar system, at its distance from the center, travels at roughly 828,000 kilometers per hour. That seems incredibly fast, and it is, yet it still takes about 230 million years to complete a single orbit around the galaxy. This vast loop is sometimes called a galactic year. Since the Sun and Earth formed about 4.5 billion years ago, we've completed only about 20 circuits around the Milky Way. The last time we were in this part of our galactic orbit, the supercontinent Pangaea was just beginning to break apart, and the age of dinosaurs had not yet begun. Understanding the Milky Way's structure is an ongoing challenge. Dust clouds obscure vast regions, especially toward the galactic center. Stars blend together at great distances. For decades, astronomers couldn't even agree on how many spiral arms the galaxy has. Some observations suggested 4 major arms. Others indicated 2. And still others found evidence of fragmentary arm segments that twist and split in unexpected ways. The truth, as revealed by increasingly detailed observations, is that the Milky Way's spiral structure is more complex and irregular than textbook diagrams suggest. The arms are not fixed structures but rather density waves, regions where stars and gas temporarily bunch together, triggering new star formation as they pass through. These patterns move at a different speed than the stars themselves, like a traffic jam that propagates along a highway even though individual cars enter and leave the congestion. From our position inside the disk, the Milky Way appears as that familiar band of light across the sky. But in visible wavelengths, we can see only a tiny fraction of what's truly there. Much of the galaxy is hidden behind curtains of interstellar dust. Dark clouds of microscopic particles that absorb and scatter starlight. To peer through these veils, astronomers use infrared telescopes, which can detect the heat radiation from stars and gas clouds even when visible light is blocked. Radio telescopes map the distribution of cold hydrogen gas, revealing structures invisible to optical instruments. X-ray and gamma-ray observatories detect high-energy phenomena associated with supernova remnants, black holes, and other exotic objects. Each wavelength reveals a different face of the galaxy, and only by combining observations across the electromagnetic spectrum can we begin to see the Milky Way in its full complexity. One of the most remarkable aspects of the Milky Way is how much of it we cannot see at all, not because of dust, but because it simply doesn't emit light. This brings us to one of the greatest mysteries in modern astronomy. Our galactic home's hidden mass, the Milky Way, has a secret. Most of what holds our galaxy together is completely invisible. It doesn't shine, doesn't reflect light, doesn't emit radio waves or X-rays. It passes through ordinary matter as if nothing were there. And yet, without it, the galaxy would fly apart into the void. This mysterious substance is called dark matter, and it makes up the vast majority of the Milky Way's mass. The story of dark matter begins with a puzzle about galactic rotation. In the 1930s, astronomer Fritz Zwicky noticed something odd about galaxy clusters. The galaxies within these clusters were moving far too fast. Based on the amount of visible matter present, they should have long ago escaped each other's gravitational pull and dispersed into space. Yet the clusters remained bound. Zwicky proposed that some unseen matter must be providing additional gravity to hold them together. For decades, this idea remained on the fringes of astronomy. Then, in the 1970s, astronomer Vera Rubin and her colleagues made detailed observations of spiral galaxies, including the Milky Way. They measured how fast stars were orbiting at various distances from the galactic center. According to Newton's laws of motion and gravity, stars farther from the center should orbit more slowly, just as the outer planets in our solar system move more leisurely around the sun. The gravitational pull should weaken with distance, causing orbital speeds to drop. But that's not what Rubin found. Instead, stars in the outer regions of spiral galaxies were moving almost as fast as those closer to the center. The rotation curves, as these graphs of orbital velocity versus distance are called, remained flat instead of declining. This was impossible to explain using only the visible matter. There simply wasn't enough gravitational pull from the stars, gas, and dust to account for these high speeds. The only explanation that fit the observations was that galaxies are embedded in vast halos of invisible matter. This dark matter extends far beyond the visible disk, providing the gravitational scaffolding that holds everything together. In the Milky Way, astronomers estimate that dark matter outweighs all the visible matter by a factor of at least 10 to 1. Some estimates suggest the ratio could be even higher. While the stars, gas, and dust we can observe account for perhaps 10% of the galaxy's total mass, the remaining 90% lurks unseen in the dark matter halo. Recent studies have attempted to weigh the Milky Way more precisely. By observing the motions of globular clusters, those ancient spherical collections of stars that orbit far out in the halo, astronomers can infer the total gravitational mass of the galaxy. The faster these clusters move, the more massive the galaxy must be to keep them bound. Using data from the Hubble Space Telescope and the European Space Agency's Gaia satellite, researchers have estimated the Milky Way's total mass at approximately 1.5 trillion times the mass of our Sun. Of this immense total, only a tiny fraction comes from the stars. The supermassive black hole at the center contributes about 4 million solar masses, a substantial number but still only a minuscule percentage of the whole. Most of the galaxy's weight is locked up in the invisible dark matter halo. But what is dark matter? The honest answer is that we don't know. It's not ordinary matter made of protons, neutrons, and electrons. Experiments have ruled out many possibilities. It doesn't appear to be vast numbers of dim stars or planet-sized objects, because such objects would occasionally pass in front of background stars and cause brief brightenings through gravitational lensing, and these events are too rare to account for all the missing mass. It doesn't seem to be clouds of cold gas, which would absorb light at specific wavelengths and betray their presence. The leading hypothesis is that dark matter consists of exotic subatomic particles that interact very weakly, if at all, with normal matter except through gravity. These particles, if they exist, were produced in the early universe and have been streaming through space ever since, clumping together under gravity to form the large-scale structure we observe. Countless trillions of them might be passing through your body every second, without leaving any trace. Physicists have built increasingly sensitive detectors deep underground, hoping to catch the rare interaction of a dark matter particle with an atomic nucleus. But so far, these searches have come up empty. The nature of dark matter remains one of the greatest unsolved problems in physics. In 2025, researchers analyzing data from the optical gravitational lensing experiment reported detecting a small core structure in the Milky Way's dark matter halo, a region about 282 parsecs across where the dark matter density appears higher than in surrounding areas. This finding, if confirmed, could provide clues about the properties of dark matter and how it behaves on small scales. Other studies have suggested the dark matter halo might extend almost 2 million light-years from the galactic center, more than 10 times the diameter of the visible disk, encompassing our satellite galaxies like the Magellanic Clouds, and possibly reaching partway to the Andromeda Galaxy. Alternative theories have been proposed to explain the rotation curves without invoking dark matter. These theories suggest that our understanding of gravity might be incomplete or incorrect on galactic scales. Perhaps gravity behaves differently at very low accelerations or across vast distances than Einstein's general relativity predicts. Several modified gravity theories have been developed, with names like M1 for modified Newtonian dynamics. While these alternatives can explain some observations, they struggle to account for the full range of evidence, including gravitational lensing by galaxy clusters, the cosmic microwave background radiation, and the formation of large-scale structure in the universe. Dark matter, despite its mysterious nature, remains the most successful explanation. Regardless of what dark matter turns out to be, its presence is undeniable. The Milky Way, like all galaxies, is primarily a structure of invisible matter. The stars we see, the planets we know, the gas and dust, and everything we can touch or observe directly, all of it amounts to just a few % of what's really there. We live on the luminous surface of something much larger and stranger. The galaxy's true skeleton is invisible, a vast web of dark matter that shaped the formation of the disk, guided the infall of gas, and continues to govern the orbits of every star. Without this hidden scaffolding, our galaxy would not exist. The stars would have scattered into the emptiness between galaxy clusters long ago. We owe our existence to the gravitational embrace of the unseen. The Galactic Center and Sagittarius A. At the heart of the Milky Way, hidden behind thick clouds of gas and dust, lies one of the most extreme environments in the galaxy. Here, in a region called Sagittarius A, stars orbit at tremendous speeds around an invisible monster. This is the Galactic Center, home to a supermassive black hole with a mass over 4 million times that of the Sun, compressed into a region smaller than the orbit of Mercury. For most of human history, the Galactic Center was completely unknown. The constellation Sagittarius, toward which the center lies, shows no obvious concentration of stars to the naked eye. Dust clouds completely obscure the view in visible light. It wasn't until the development of radio and infrared astronomy in the 20th century that the true nature of this region began to be revealed. In the 1950s, radio astronomers detected a powerful source of radio waves emanating from the direction of Sagittarius. They named it Sagittarius A, and the brightest component right at the galaxy's heart became Sagittarius A, pronounced A star. But what was producing these radio waves? The answer came from decades of patient observation. Beginning in the 1990s, astronomers using large infrared telescopes in Chile and Hawaii began tracking individual stars very close to Sagittarius A. They took images night after night, year after year, measuring the positions of these stars with extraordinary precision. Over time, the stars' motions traced out elliptical orbits. One star, designated S2, completes an orbit in just 16 years, swinging so close to Sagittarius A that it reaches speeds of nearly 5,000 kilometers per second, about 2% the speed of light. By applying Newton's and Einstein's laws of gravity to these orbits, astronomers could calculate the mass of whatever object lay at the center. The result was staggering. There had to be something with more than 4 million solar masses packed into a region no larger than our inner solar system. The only object that could be so massive and so compact is a black hole. This work, led by Reinhard Genzel and Andrea Ghez, earned them the Nobel Prize in Physics in 2020. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape once it crosses a boundary called the event horizon. Supermassive black holes, containing millions or billions of solar masses, lurk at the centers of most large galaxies. They form through mechanisms still not fully understood, possibly by the direct collapse of massive gas clouds in the early universe, or through the merger of smaller black holes and the steady accretion of matter over billions of years. Sagittarius A is, by galactic standards, a quiet black hole. Most of the time, it emits very little radiation. Matter falling into it does so at a slow trickle, producing only weak flickers of light and radio waves. This is fortunate for us because a black hole that's actively feeding can produce enormous amounts of radiation, including X-rays and gamma rays that could be harmful to life on nearby planets. Some galaxies have black holes so actively feeding that they outshine the entire galaxy around them. These are called quasars. And they were far more common in the early universe when galaxies were younger and gas was more abundant. But Sagittarius A wasn't always so quiet. In 2025, scientists using artificial intelligence to analyze millions of simulations discovered that the Milky Way's supermassive black hole is spinning at nearly its maximum possible rate. A spinning black hole drags space-time around with it in a phenomenon called frame dragging. The faster it spins, the more it warps the space around it. This rapid rotation suggests that Sagittarius A has been fed substantial amounts of material in the past, possibly in violent episodes when the galaxy collided with smaller galaxies or when large gas clouds fell inward toward the core. Evidence for such past activity comes from structures called the Fermi bubbles. Discovered only in 2010, these are enormous lobes of high-energy gamma radiation extending tens of thousands of light-years above and below the galactic plane. They're invisible to optical telescopes, but they glow brilliantly in gamma-ray observations from space. The bubbles are thought to be the remnants of a massive outburst from the galactic center, either from the black hole itself or from an intense period of star formation in the core. When a supermassive black hole actively feeds, it can eject powerful jets of matter and energy perpendicular to its accretion disk. These jets plow into the surrounding gas, creating shock waves and enormous cavities. The Fermi bubbles may be the faded echoes of such an event that occurred millions of years ago. Another recent discovery adds to this picture of past violence. Astronomers have detected strange structures in nearby gas clouds that appear to be light echoes, reflections of bright radiation that illuminated the clouds sometime in the past few hundred years. These echoes suggest that Sagittarius A flared much more brightly in the recent past than it does today. Perhaps a gas cloud or even a star wandered too close and was torn apart, causing the black hole to temporarily brighten as it fed on the disrupted material. The galactic center is also home to a dense population of stars. Infrared observations reveal clusters of massive, young stars orbiting near Sagittarius A. These stars shouldn't be there. The environment close to a supermassive black hole is chaotic and violent, not conducive to star formation. Yet there they are, massive blue giants only a few million years old. How they formed remains a puzzle. Perhaps they were born farther out and their orbits migrated inward. Or perhaps there are ways to form stars even in such hostile conditions that we don't yet understand. The galactic center also contains a bar-shaped structure, a thick, elongated concentration of stars cutting across the middle of the galaxy. When astronomers look toward the core in infrared light, piercing through the dust, they see not a perfect circle but a glowing bridge of stars. This bar rotates slowly, and its gravitational pull shapes the inner spiral arms. Bars are common in spiral galaxies, and they play an important role in galactic evolution. They can funnel gas inward, feeding star formation and possibly feeding the central black hole. Over billions of years, the bar's strength can wax and wane, and it may even dissolve and reform as the galaxy evolves. The central bulge surrounding the black hole is not a simple sphere, but has a complex three-dimensional structure. Recent studies have revealed it to be somewhat peanut-shaped when viewed edge-on, swelling in the middle and narrowing at the ends. This geometry is sculpted by the bar's gravity, which causes stars to move in intricate orbits that, when combined, create this peculiar shape. Despite being hidden behind 27,000 light-years of dust and gas, the galactic center continues to reveal its secrets. New telescopes operating in wavelengths unaffected by dust, powerful computers capable of simulating black hole accretion and stellar dynamics, and years of patient observation are slowly bringing this region into focus. We may never see Sagittarius A directly with visible light, but through radio waves, infrared, X-rays, and gamma rays, we're building an ever more detailed picture of the monster at the heart of our galaxy. Spiral arms and star formation. If you could somehow view the Milky Way from above, from a vantage point high above the galactic plane, one of the most striking features would be the spiral arms. These great sweeping curves, traced out by clusters of bright young stars and glowing nebulae, give the galaxy its characteristic pinwheel appearance. But the spiral arms are not what they seem. They're not like the arms of a spinning pinwheel, fixed structures rotating through space. Instead, they're patterns, waves of density moving through the disk that temporarily compress gas and trigger bursts of star formation. Imagine traffic on a busy highway. Sometimes, for no obvious reason, traffic slows down in one section. Cars bunch up, creating a jam. As each car reaches the congested area, it slows down, passes through, and then speeds up again. The jam itself moves backward along the highway, even though individual cars are moving forward. The traffic jam is a density wave, a pattern that exists independently of the objects moving through it. Spiral arms work similarly. They're regions where stars, gas, and dust are temporarily more concentrated. As the galaxy rotates, material moves into these density waves, slows down slightly due to gravitational interactions, and then moves out again. The density wave itself rotates at a different speed than the stars. In the Milky Way, the pattern speed of the spiral arms is such that, at certain distances from the center, stars spend more time inside the arms than outside. This orbital resonance can have significant effects on star formation and even on the climates of planets. Our Sun orbits near what's called the co-rotation radius, a special distance where the speed of stars matches the pattern speed of the spiral arms. This means the Sun tends to stay between the major arms in the relatively calm Orion spur, avoiding frequent passages through the denser spiral arms where supernovae are more common and gravitational disturbances more frequent. This may be another piece of cosmic luck that has allowed life on Earth to develop relatively undisturbed. When gas clouds enter a spiral arm, they're compressed by the increased density. This compression can push clouds beyond a critical threshold, causing them to collapse under their own gravity and begin forming stars. This is why spiral arms glow so brightly with young, hot stars. These massive stars are blue and luminous, but they burn through their fuel quickly, living for only a few million years. By the time they die in spectacular supernova explosions, they've already drifted out of the spiral arm where they were born. The arm remains, ready to compress the next wave of gas clouds and start the process anew. Star formation is one of the most fundamental processes in the universe. Without it, there would be no second-generation stars enriched with heavy elements, no rocky planets, no chemistry complex enough to support life. In the Milky Way, stars are born in cold, dark clouds of molecular gas. These clouds, composed mostly of molecular hydrogen, with traces of other compounds like carbon monoxide, dust, and complex organic molecules, can be enormous, spanning hundreds of light years and containing enough material to form thousands or even millions of stars. One of the largest molecular clouds in the Milky Way is in the constellation Orion, visible to the naked eye as a fuzzy patch in Orion's sword. This is the Orion Nebula, a stellar nursery just 1,500 light-years away, relatively close by galactic standards. Infrared observations reveal hundreds of newly forming stars within the nebula, still surrounded by disks of dust and gas from which planets may eventually form. The brightest stars in the nebula are only a few million years old, infants on cosmic timescales. Within these clouds, gravity slowly draws material together. Small clumps become denser, pulling in more gas from their surroundings. As a clump contracts, it heats up. The center grows hotter and denser, eventually forming a protostar, a warm core glowing with the heat of gravitational collapse. Material continues to fall inward, spiraling down through an accretion disk. Jets of gas shoot outward from the poles driven by magnetic fields and the intense radiation from the growing star. For tens of thousands or millions of years, this continues. The protostar grows more massive, its core growing hotter. Eventually, if the mass is sufficient, the core reaches temperatures and pressures high enough for nuclear fusion to ignite. Hydrogen atoms fuse into helium, releasing tremendous energy. This is the moment a star is truly born. The outward pressure from fusion balances the inward pull of gravity, and the star settles into a stable state that can last for millions or even trillions of years, depending on its mass. The most massive stars, dozens of times the mass of the Sun, shine with brilliant blue light. They're rare but spectacular, pumping out ultraviolet radiation that ionizes nearby gas and makes it glow in vivid reds and blues. These massive stars live fast and die young, exhausting their fuel in just a few million years. When they explode as supernovae, they blast heavy elements into space, enriching the interstellar medium with the raw materials for future generations of stars and planets, the shock waves. From these explosions can also trigger new star formation by compressing nearby clouds. Lower mass stars like the Sun are far more common and much longer lived. The Sun will shine steadily for about 10 billion years, slowly converting hydrogen into helium in its core. When it exhausts its hydrogen, it will swell into a red giant, eventually shedding its outer layers to form a planetary nebula, while its core collapses into a white dwarf, a dense ember slowly cooling over billions of years. The rate of star formation in the Milky Way has not been constant over time. In the early universe, when the galaxy was younger and gas was more abundant, star formation was more vigorous. Billions of years ago, the Milky Way was more active, bursting with fresh stars born from dense, collapsing clouds. But as time passed, more and more of the galaxy's gas became locked up in stars, or was heated and dispersed by supernova explosions and stellar winds. Today, the Milky Way forms new stars at a rate of perhaps 1 to 3 solar masses per year, a modest pace compared to some galaxies that are undergoing starbursts and forming stars hundreds of times faster. The spiral arms continue to be the primary sites of this ongoing star formation. In a new radio color image of the Milky Way released in October 2025, astronomers cataloged 98,000 radio sources across the southern galactic plane, revealing supernova remnants, pulsars, and star-forming regions in unprecedented detail. This map, created by processing more than 40,000 hours of observational data, shows the galaxy's birth and death of stars laid out in radio wavelengths. It's a different view of the Milky Way, one that highlights the dynamic processes shaping our galaxy even now. The interplay between star formation and star death creates a complex ecosystem within the galaxy. Stars are born from gas clouds, live their lives, and return much of their material to space, enriched with heavy elements forged in their cores and in supernova explosions. This recycled material joins the interstellar medium, mixing with pristine gas to form the next generation of stars. Over billions of years, the galaxy's composition has evolved. The earliest stars contained almost no heavy elements, just hydrogen and helium left over from the Big Bang. But each generation of stars has enriched the mix. The Sun formed about 4.5 billion years ago from gas that had already been processed through earlier generations of stars, giving it a healthy complement of carbon, oxygen, iron, and other elements essential for rocky planets and life. The galactic warp and wave. The Milky Way is not a perfect, flat disk. If you could view it edge-on, you'd notice something odd. The disk doesn't lie flat like a geometric plane. Instead, it bends, warping upward on one side and downward on the other, like a vinyl record left too close to a heater. This galactic warp has been known for decades, but recent observations have revealed something even more surprising. The galaxy isn't just warped, it's rippling. In October 2025, astronomers analyzing data from the European Space Agency's Gaia Space Telescope announced the discovery of a massive wave traveling through the Milky Way. This wave, spanning tens of thousands of light years, undulates through the galactic disk like a slow-motion ripple on the surface of a pond. The study tracked thousands of bright stars and measured their positions above and below the expected plane of the disk. These stars revealed a clear pattern. In some regions, stars sit higher than expected. In others, they dip lower, and this pattern extends coherently across large swaths of the galaxy. What causes this wave is still uncertain. It could be the result of a gravitational interaction with a passing dwarf galaxy, perhaps one of the Magellanic Clouds that orbit the Milky Way. When a smaller galaxy passes nearby, its gravity can tug on the disk, setting up oscillations that persist for millions of years. Alternatively, the wave might be generated internally, perhaps by instabilities in the disk, or by the gravitational influence of the bar at the galactic center. The Milky Way's disk is not a rigid structure. It's a dynamic system, responsive to gravitational perturbations, and it can sustain waves and oscillations much like a drumhead vibrates when struck. The warp itself, the large-scale bend in the disk, is thought to arise from the combined gravitational pull of the Magellanic Clouds and possibly from the distribution of dark matter in the halo. The large and small Magellanic Clouds are two dwarf galaxies visible from the southern hemisphere as faint, fuzzy patches of light. They've long been considered satellite galaxies orbiting the Milky Way, but recent measurements of their velocities suggest they might be on their first close pass, newcomers recently captured by our galaxy's gravity. As they orbit, their gravitational pull tugs on the outer reaches of the galactic disk, bending it out of shape. Behind the Magellanic Clouds stretches a long stream of hydrogen gas, stripped from the clouds by tidal forces. This Magellanic stream wraps around the southern sky, an immense ribbon of gas hundreds of thousands of light-years long, invisible to the eye but prominent in radio observations. Material from this stream may eventually fall into the Milky Way, providing fresh fuel for future star formation. The interaction between the Milky Way and the Magellanic Clouds is ongoing, a slow dance that will eventually lead to their full merger, though that lies many billions of years in the future. The discovery of the galactic wave adds to a growing picture of the Milky Way as a dynamic, living structure. Gaia has transformed our understanding of the galaxy. Launched in 2013, Gaia spent over a decade scanning the sky, measuring the precise positions, distances, and motions of more than 2 billion stars in January 2025. The spacecraft completed its observing mission, its fuel nearly exhausted. But the data it collected will keep astronomers busy for decades. Gaia's measurements are astonishingly precise. It can measure stellar positions to within a few millionths of a degree, equivalent to measuring the width of a human hair from 1,000 kilometers away. These precise measurements allow astronomers to map the galaxy in 3 dimensions and to trace the motions of stars through space, not just toward or away from us, but also across the sky. This full 3-dimensional velocity information is crucial for understanding the structure and history of the galaxy. One of Gaia's most remarkable contributions has been the discovery of stellar streams, faint trails of stars stretching across the sky. These streams are the remnants of smaller galaxies and star clusters that wandered too close to the Milky Way and were torn apart by tidal forces. As these objects orbit, their stars are stretched into long, thin lines, like taffy pulled by invisible hands. By mapping these streams, astronomers can reconstruct the galaxy's history, identifying past mergers and tracing the paths of long-dead dwarf galaxies whose stars now mingle with our own. The Milky Way has grown through accretion, gradually consuming smaller galaxies over billions of years. One of the largest known mergers was with a dwarf galaxy called Gaia Enceladus, which collided with the Milky Way around 10 billion years ago. This collision was catastrophic, disrupting both galaxies and adding billions of stars to the Milky Way's halo. Many of the metal-poor stars now orbiting in the halo may have originated in Gaia Enceladus or other absorbed dwarf galaxies. Their chemical signatures and unusual orbits give them away as immigrants from elsewhere. Even today, the Milky Way is in the process of consuming smaller galaxies. The Sagittarius dwarf elliptical galaxy, discovered in 1994, is being pulled apart by the Milky Way's gravity. Its stars are spread into long streams that loop around the sky. Over the next few billion years, these stars will fully merge with the Milky Way, becoming indistinguishable from the general stellar population. It's a slow, gentle cannibalism, played out over hundreds of millions of years. The galactic disk also bobs and wobbles as the galaxy rotates. The disk is not perfectly flat, and it's not perfectly stable. Gravitational interactions with satellite galaxies, with clumps of dark matter, and even with the galaxy's own spiral arms, can set the disk oscillating vertically, like a flag waving slowly in a breeze. Our solar system participates in this motion, drifting above and below the galactic plane in a cycle that takes tens of millions of years. Some researchers have speculated that these oscillations might influence the frequency of comet impacts on Earth, though the evidence for such a connection remains inconclusive. All of these discoveries, the warp, the wave, the stellar streams, paint a picture of the Milky Way as far more complex and dynamic than earlier generations of astronomers imagined. It's not a static, unchanging structure, but a galaxy shaped by collisions, mergers, gravitational interactions, and internal processes. It's a galaxy with a history, a story written in the motions and compositions of its stars, ancient mergers and stellar streams. The Milky Way is a composite, a patchwork of material gathered from many sources over billions of years. In its halo orbit stars that were not born here, but in smaller galaxies that have long since been dismantled. By studying these ancient stars, astronomers can peer back into the galaxy's past and reconstruct the violent events that shaped it. The oldest stars in the galaxy are found primarily in the halo and in globular clusters. These stars are metal poor, meaning they contain very few elements heavier than hydrogen and helium. In astronomical parlance, metals refers to all elements heavier than helium, including carbon, oxygen, iron, and so on. The very first stars in the universe, formed from the primordial gas left over from the Big Bang, contained no metals at all. They were made purely of hydrogen and helium. When these first stars died, many in supernova explosions, they enriched the surrounding gas with newly forged elements. Subsequent generations of stars incorporated these metals, gradually increasing the metal content with each stellar generation. By measuring the metal content of a star, astronomers can estimate its age. Metal-poor stars are likely to be very old, formed before the galaxy had been enriched by many generations of supernovae. The most metal-poor stars known contain less than 1/10,000th the iron content of the Sun. These stars are time capsules, preserving the conditions of the early universe. Many of these ancient stars move on unusual orbits, high above the galactic plane or in retrograde, orbiting opposite to the galaxy's main rotation. These strange orbits are clues to their origins. Stars born in the Milky Way's disk orbit more or less in the same direction as the disk rotates, like cars on a circular racetrack. But stars with tilted or retrograde orbits likely came from elsewhere, captured when the Milky Way merged with smaller galaxies billions of years ago. The Gaia mission has revolutionized the study of these ancient mergers. By mapping the three-dimensional positions and velocities of millions of stars, Gaia can identify groups of stars that share a common motion and origin. Several major merger events have been discovered this way. The Gaia and Enceladus merger mentioned earlier added many stars to the inner halo and may have reshaped the early structure of the galaxy. Another event, sometimes called the Kraken merger, may have been even larger, occurring very early in the galaxy's history and contributing significantly to the buildup of mass. These mergers were not gentle. When galaxies collide, their stars rarely hit each other. Stars are so small and so widely spaced that direct collisions are virtually impossible. But the galaxy's gravitational fields interact strongly, pulling and distorting both systems. Stars are flung into new orbits. Gas clouds collide and compress, triggering bursts of star formation. Over time, the smaller galaxy is torn apart, its stars scattered into the larger galaxy's halo or disk, and the two systems merge into one. The Milky Way has likely consumed dozens of smaller dwarf galaxies over its lifetime. Each merger leaves traces, streams of stars with similar ages, compositions, and motions. moving together through the halo like ghostly remnants of their parent galaxy. By tracing these streams backward in time, astronomers can reconstruct the orbits of the destroyed dwarfs and learn about the galaxy's gravitational potential. Globular clusters, those dense spheres of hundreds of thousands of stars, are also products of this violent history. The Milky Way has more than 150 globular clusters orbiting in its halo. They're incredibly old, with ages of 12 billion years or more, making them some of the oldest objects in the galaxy. Many globular clusters probably formed in dwarf galaxies and were later captured when those dwarfs were absorbed by the Milky Way. The clusters survived the merger intact, protected by their own self-gravity, while the rest of the dwarf galaxy was shredded. Some stars in the Milky Way are even older than the disk itself. The disk, the flat spiral structure we think of as the main body of the galaxy, formed gradually over time as gas settled into a rotating plane. But some stars in the halo formed earlier, when the galaxy was still a loose, chaotic cloud of gas and dark matter slowly collapsing under gravity. These stars are the elders, silent witnesses to the galaxy's birth. Their compositions reveal the chemical makeup of the universe when it was less than 1 billion years old, and their orbits trace the early dynamics of galactic assembly. One of the most exciting developments in galactic archaeology has been the ability to combine Gaia's positional data with spectroscopic observations that measure stars' chemical compositions. By mapping both the motions and the chemistry of stars, astronomers can identify families of stars that share a common origin. It's like detective work, piecing together clues from light that has traveled for thousands of years to reach our telescopes. Stellar streams are particularly valuable for studying the galaxy's dark matter distribution. The shape and motion of a stream depend on the gravitational field it moves through. By modeling streams precisely and comparing the models to observations, astronomers can infer the distribution of mass in the galaxy, including the invisible dark matter. Some streams are narrow and tight, while others are broad and diffuse, and these differences tell us about the clumpiness and structure of the dark matter halo. There's also evidence that the Milky Way experienced a major growth spurt between 7 and 10 billion years ago, when multiple dwarf galaxies fell in and merged within a relatively short time. This period of intense merging may have thickened the disk and contributed to the formation of the thick disk component. The thick disk contains stars that are older and more metal-poor on average than those in the thin disk, and their orbits are more random and less confined to the plane. This suggests they were stirred up by gravitational interactions during the merger period. The story of the Milky Way is one of growth through accretion, of slow assembly from smaller pieces. The galaxy we see today is the product of billions of years of collisions, mergers, and gradual infall of gas and smaller galaxies. It's not a pristine, primordial object, but a composite, stitched together from the remains of many smaller systems. And the process isn't over. The galaxy continues to grow, pulling in gas from the intergalactic medium, stripping stars from dwarf galaxies, and slowly assembling more mass. In a sense, the Milky Way is still under construction, a work in progress that will continue evolving for billions of years to come. Our solar system's journey. Our solar system is not a fixed point in space. It's in motion, orbiting the galactic center at nearly 830,000 kilometers per hour, fast enough to circle the globe in under 3 minutes. And yet, despite this tremendous speed, it takes roughly 230 million years to complete a single orbit around the galaxy. This is the timescale of galactic motion, vast and slow by human standards, but swift on cosmic scales. We're located about 27,000 light-years from the galactic center, roughly halfway out from the core to the edge of the visible disk. Our neighborhood is called the Orion Spur, sometimes referred to as the Orion Arm, though it's more accurately described as a minor arm or spur, a smaller feature nestled between two major spiral arms. To one side lies the Sagittarius Arm, sweeping inward toward the galactic center. To the other is the Perseus Arm, stretching outward. The Orion Spur is less densely populated than the major arms, with fewer massive stars and less active star formation. This relative quietness may have been important for the development of life on Earth. The major spiral arms are busy places. They're regions of intense star formation, filled with massive young stars that pump out ultraviolet radiation and end their brief lives in supernova explosions. A planet orbiting a star deep within a major arm would be exposed to higher levels of radiation and would experience more frequent supernova events in its cosmic neighborhood. Some astronomers have suggested that there's a galactic habitable zone, a region of the galaxy where conditions are most favorable for life. This zone would be far enough from the violent galactic center, but not so far out in the metal-poor outskirts that planets have trouble forming. It would also avoid the most intense regions of star formation. The Orion Spur seems to fit these criteria nicely. Our position near the co-rotation radius is also significant. The co-rotation radius is the distance from the galactic center where the orbital speed of stars matches the pattern speed of the spiral arms. Inside this radius, stars orbit faster than the spiral pattern and frequently pass through the arms. Outside, they orbit slower and also cross the arms regularly. But right at the co-rotation radius, stars tend to drift along with the spiral pattern, spending most of their time between the arms. The Sun appears to orbit close to this special radius, which means we spend long periods in the relatively calm space between the major arms, possibly reducing our exposure to the hazards associated with spiral arm passages. As the Sun orbits, it doesn't move in a perfect circle. The gravitational pull of the galaxy's mass, including the central bulge, the disk, and the dark matter halo, causes the Sun to oscillate vertically, drifting above and below the galactic plane in a gentle wave. This vertical motion has a period of roughly 30 to 40 million years. Currently, we're fairly close to the galactic plane, within about 60 light-years of the midplane, but over time we'll drift upward, reach a peak several hundred light-years above the plane, then fall back down, cross the plane, descend to a similar distance below it, and then rise again. Some researchers have speculated that these vertical oscillations might correlate with geological events on Earth, perhaps influencing the frequency of comet impacts or the exposure to cosmic rays. The idea that as the solar system passes through the denser regions of the galactic plane, gravitational interactions with molecular clouds or spiral arms might perturb the Oort cloud, a distant shell of comets surrounding the solar system, sending some of them plunging toward the inner planets. However, the evidence for such correlations remains inconclusive, and many astronomers are skeptical that galactic motions have a significant impact on Earth's climate or biosphere. What is clear is that the solar system's position in the galaxy has not been constant. The last time we were in this part of our galactic orbit, the continents on Earth were in very different positions. Pangaea, the supercontinent, was just beginning to break apart. Dinosaurs had not yet emerged. The planet was dominated by reptiles and early mammal-like creatures. Since then, we've traveled a quarter of the way around the galaxy, and everything on Earth has changed dramatically. Mountains have risen and eroded. Seas have opened and closed. Entire lineages of life have appeared and gone extinct. Looking ahead, the solar system will continue its steady orbit for billions of years. The Sun is about halfway through its main sequence lifetime. In another 5 billion years, it will exhaust the hydrogen in its core and begin to swell into a red giant. But long before that, changes in the Sun's luminosity will render Earth uninhabitable. Life on Earth may have only another billion years or so before the oceans boil away. By then, the solar system will have completed 4 or 5 more orbits around the galaxy. If any descendants of humanity still exist, they may have spread to other stars, becoming a truly spacefaring species. But the Sun's orbit will continue, carrying the remnants of our solar system, whatever form they take, through the Milky Way's spiral arms. It's humbling to realize that our entire recorded history, all of human civilization, has occurred during less than 1/10,000,000th of a single galactic orbit. All the rises and falls of empires, all the discoveries and inventions, all the art and music and science have taken place while the Sun has traveled just a tiny fraction of its path around the galaxy. On cosmic scales, our history is an eye blink, a brief moment in the slow turning of the galactic wheel. Yet, in that brief moment, one species on one planet has managed to figure out where it is in the cosmos. We've mapped our galaxy, measured our motion through it, understood the forces that shape it. From our small vantage point in the Orion Spur, we've looked outward and inward, toward the distant edges and toward the hidden center, and we've begun to piece together the story of our galactic home. That's no small achievement, the Milky Way's future. The Milky Way's story is far from over. The galaxy we see today is just one chapter in a long history, and many dramatic events still lie ahead. The most significant is the coming collision with the Andromeda Galaxy. Andromeda, also known as Messier 31, is the closest large spiral galaxy to the Milky Way. It lies about 2.5 million light-years away and is visible to the naked eye as a faint smudge of light in the constellation Andromeda. For centuries, it was thought to be a nebula within our own galaxy. Only in the early 20th century did astronomers realize it was a separate galaxy, an island universe in its own right, similar in structure to the Milky Way but somewhat larger and more massive. Andromeda is moving toward us. Measurements of its light show a blue shift, indicating that it's approaching at roughly 100 kilometers per second. This might not sound like much, but over millions of years, that slow approach adds up. In about 4 to 5 billion years, the Milky Way and Andromeda will collide. Galactic collisions are not like collisions between solid objects. Stars are so small and so widely spaced that direct collisions between stars are almost unheard of. When galaxies merge, it's their gravitational fields that interact. The two galaxies will pass through each other, their shapes distorting as tidal forces stretch and pull at their structures. Long tails of stars will be flung into space. The spiral arms will be disrupted. Gas clouds will collide and compress, triggering intense bursts of star formation, turning the night sky into a blaze of brilliant young stars and colorful nebula. The first pass will be dramatic, but it won't be the end. Gravity will pull the two galaxies back together. They'll swing around each other, pass through again, and gradually the two systems will merge into a single, larger galaxy. Computer simulations suggest the merger will take several billion years to complete. Eventually, the combined system will settle into a roughly elliptical shape, a vast swarm of stars orbiting a common center of gravity. The spiral structures of both galaxies will be destroyed, replaced by a more chaotic elliptical distribution. What will happen to the solar system during this merger? Most likely, nothing catastrophic. The sun and planets will be jostled by the changing gravitational field, possibly shifted to a different orbit within the merged galaxy. But the chances of a close encounter with another star are vanishingly small. We might even get a spectacular view. During the merger, the night sky will be filled with the light of two galactic cores, bright nebulae, and countless young stars. If any intelligent life still exists on Earth, or its successor worlds, they'll witness one of the most dramatic events in cosmic history. But there's another potential future that's more concerning. In March 2025, astronomers discovered a massive spiral galaxy nearly a billion light-years away that harbors a supermassive black hole billions of solar masses in size. This black hole is powering colossal radio jets stretching 6 million light-years across, among the largest known for any spiral galaxy. Such powerful jets are usually found only in elliptical galaxies, not spirals, and the discovery has prompted astronomers to consider whether the Milky Way's central black hole could one day produce similar jets. If Sagittarius A were to become active, perhaps triggered by the infall of a large gas cloud or the disruption of a star that wandered too close, it could generate powerful jets and floods of radiation. The cosmic rays, gamma rays, and X-rays produced could wreak havoc in our solar system, increasing radiation levels and potentially causing harm to the biosphere on Earth. Such events are called active galactic nucleus episodes, or AGN episodes, and they were much more common in the early universe when gas was more abundant. The good news is that such an event is unlikely in the near future. Sagittarius A is currently very quiet, fed by only a trickle of material. For it to become highly active would require a significant influx of gas or stars, and while such events can happen, they're rare. Still, the discovery reminds us that even our own galaxy has the potential for violent behavior. Beyond the Andromeda merger, the Milky Way's even more distant future is tied to the fate of the universe itself. Observations show that the expansion of the universe is accelerating, driven by a mysterious force called dark energy. Over hundreds of billions of years, this acceleration will pull galaxy clusters apart. Eventually, the only galaxies remaining bound together will be those within a single gravitationally bound group. The Milky Way, Andromeda, and the smaller galaxies of the local group will merge into a single massive galaxy, isolated in an ever-expanding void. Trillions of years from now, star formation will have ceased. All the gas will have been used up or ejected. The last stars will burn out, leaving behind white dwarfs, neutron stars, and black holes slowly cooling in the darkness. The merged galaxy will become a ghostly relic, a vast cloud of stellar remnants drifting through an increasingly empty universe. But that fate lies so far in the future that it's almost beyond comprehension. For now, the Milky Way is a vibrant, active galaxy, still forming stars, still growing, still full of light and motion and possibility. Mapping our galaxy. One of the greatest challenges in astronomy is mapping the galaxy we live inside. From our position within the disk, surrounded by stars and dust, it's difficult to see the overall structure. It's as though we're trying to map a vast city while standing in the middle of a busy street with fog all around. Nevertheless, through patient observation and increasingly sophisticated technology, astronomers have pieced together a remarkably detailed picture of the Milky Way. The transformation in our understanding has been dramatic. A century ago, astronomers didn't even know the Sun was far from the center of the galaxy. They thought the Milky Way was relatively small and that the Sun was near its heart. It was Harlow Shapley who, in the 19-teens, realized the truth. By studying the distribution of globular clusters, he showed that they were centered not on the Sun, but on a point far away in the direction of Sagittarius. The Sun, he concluded, was far from the galactic center out in the suburbs. His measurements of the galaxy's size, about 100,000 light-years across, have held up remarkably well. But mapping the detailed structure of the Milky Way required new tools. Dust clouds obscure much of the galaxy in visible light, especially toward the center and along the galactic plane. Radio astronomy, developed in the mid-20th century, provided a way to peer through the dust. Radio waves can pass through dust unimpeded, allowing astronomers to map the distribution of hydrogen gas throughout the galaxy. By measuring the Doppler shifts of radio emissions from hydrogen clouds at different galactic longitudes, astronomers could infer the galaxy's rotation curve and map the spiral arms. Infrared astronomy, which observes heat radiation rather than visible light, also proved crucial. Infrared light can penetrate dust much better than visible light. In the 1980s and 90s, infrared satellites like IRAS and Spitzer mapped the galaxy at these wavelengths, revealing the central bar and bulge in detail and identifying regions of active star formation hidden behind dust clouds. But the real revolution came with the Gaia mission. Launched in 2013 by the European Space Agency, Gaia was designed to measure the positions and motions of stars with unprecedented precision. It orbits the Sun at a gravitationally stable point called L2, about 1.5 million kilometers from Earth, spinning slowly and scanning the sky continuously. Over its decade-long mission, Gaia observed each of its target stars an average of 70 times, building up a three-dimensional map of stellar positions and motions. Gaia's precision is staggering. It can measure angles as small as a few millionths of a degree, equivalent to measuring the width of a human hair from 1,000 kilometers away. This allows it to detect the tiny apparent shifts in star positions caused by parallax, the change in a star's position as Earth orbits the Sun. By measuring parallax, Gaia can determine distances to stars directly, without relying on less certain methods like brightness estimates. For more than 2 billion stars, Gaia measured not only their positions but also their motions across the sky and their velocities toward or away from us. This full six-dimensional information, 3 position coordinates, and 3 velocity components, allows astronomers to trace stars' orbits through the galaxy, both forward and backward in time. It's like being able to watch a movie of the galaxy's evolution, seeing how stars move and interact over millions of years. The data releases from Gaia have been transformative. The first major data release in 2016 contained positions and brightness for over 1 billion stars. Subsequent releases added parallaxes, velocities, and detailed information about stellar properties like temperature and composition. Researchers have used Gaia data to discover stellar streams, identify thousands of asteroids, refine the galaxy's rotation curve, map the warp and flare of the disk, and much more. In January 2025, Gaia completed its sky scanning phase, having accumulated more than 3 trillion observations. 2 more major data releases are planned for around 2026 and the end of the decade. Each release will include even more detailed information, helping astronomers refine the three-dimensional map of the galaxy and understand its history and evolution. Other surveys have complemented Gaia's work. In October 2025, astronomers released a stunning new radio image of the Milky Way, the largest low-frequency radio color image ever assembled. This image, covering the southern galactic plane, cataloged 98,000 radio sources, including supernova remnants, pulsars, and star-forming regions. It was created by processing data from 2 extensive radio surveys, requiring more than 40,000 hours of supercomputer time. The image reveals the galaxy in radio wavelengths, showing structures invisible to optical telescopes and providing new insights into the birth and death of stars. Radio telescopes have also been used to map the distribution of molecular gas throughout the galaxy, identifying vast clouds where stars are forming. Surveys in infrared, X-ray, and gamma-ray wavelengths have revealed different aspects of the galaxy's structure and activity. By combining observations across the electromagnetic spectrum, astronomers are building a comprehensive, multi-wavelength portrait of the Milky Way. One of the most ambitious upcoming projects is the Square Kilometre Array, or SKA, a next-generation radio telescope currently under construction in Australia and South Africa. When completed, the SKA will be the world's largest and most sensitive radio telescope, capable of mapping the Milky Way's structure in exquisite detail, detecting faint signals from the earliest epochs of star formation, and studying the properties of dark matter and dark energy. The SKA will surpass even the impressive images produced in 2025, pushing the boundaries of what we can learn about our galaxy. These mapping efforts are not just about making pretty pictures, though the images are indeed beautiful. They're about understanding the physical processes that shape galaxies, tracing the flow of matter and energy, and learning how systems like the Milky Way form and evolve over cosmic time. Every new observation adds a piece to the puzzle, and gradually, the picture becomes clearer. Life in the galaxy, one of the most profound questions we can ask about the Milky Way, is whether we're alone. With hundreds of billions of stars and likely at least as many planets, the galaxy seems vast enough to harbor many worlds where life could exist. But finding evidence of life beyond Earth remains one of the greatest challenges in science. The search begins with understanding where life might arise. Not every location in the galaxy is equally hospitable. The galactic center, with its dense concentration of stars, high levels of radiation, and frequent supernova explosions, seems like a harsh environment for life. Planets there would be bombarded with radiation, and gravitational disruptions could destabilize planetary systems. The far outer reaches of the galaxy are also challenging. These regions have fewer heavy elements, making it harder for rocky planets to form. Life as we know it requires elements like carbon, oxygen, nitrogen, and iron, all of which are produced in stars and dispersed by supernova. In the early universe, and in the metal-poor outer regions of galaxies, these elements are scarce. The concept of a galactic habitable zone suggests there's a sweet spot, a region of the galaxy where conditions are most favorable for life. This zone would be far enough from the galactic center to avoid the intense radiation and stellar crowding, but not so far out that heavy elements are too scarce. It would also, ideally, avoid regions of intense star formation, where supernova are common. Some estimates place the galactic habitable zone in a broad ring roughly halfway between the center and the edge, exactly where the Sun happens to be. Of course, the concept of a galactic habitable zone is somewhat speculative. Life might be more resilient and adaptable than we imagine. Perhaps it can arise even in environments we consider hostile. Or perhaps the specific conditions required for complex, intelligent life are so rare that only a tiny fraction of the galaxy is suitable. The discovery of thousands of exoplanets, planets orbiting other stars, has revolutionized our understanding of planetary systems. Before the 1990s, the only known planets were in our solar system. Now, thanks to space telescopes like Kepler and TESS, we know that planets are common. Most stars have at least one planet, and many have multiple worlds. Planets come in a wide variety of sizes and compositions, from gas giants larger than Jupiter to rocky worlds smaller than Earth, to strange intermediate types with no analog in our solar system. Some of these planets orbit in their star's habitable zone, the region where temperatures are right for liquid water to exist on the surface. Water is thought to be essential for life, at least life as we know it. Dozens of potentially habitable planets have been discovered, though characterizing their atmospheres and surface conditions is extremely difficult. The next generation of space telescopes, including the James Webb Space Telescope already in operation and future missions like the Habitable Worlds Observatory, aim to study the atmospheres of nearby exoplanets, searching for biosignatures, chemical signs that could indicate the presence of life, such as oxygen, methane, or other gases produced by living organisms. Within the Milky Way, planetary systems form throughout the disk. As stars are born from collapsing gas clouds, they're typically surrounded by rotating disks of leftover material. Within these disks, dust grains stick together, gradually building up into larger and larger clumps. Over millions of years, these clumps grow into planetesimals, asteroid-sized bodies, and eventually into full-fledged planets. The details of this process are still being worked out, but it's clear that planet formation is a natural consequence of star formation. Some regions of the galaxy may be particularly favorable for planet formation. Areas with the right mix of elements, enough heavy elements to build rocky planets, but not so much that the environment is overly harsh, might produce planets more readily. The age of the star also matters. Very young stars are still surrounded by chaotic disks and aren't yet stable enough to have long-lived planetary systems. Very old stars formed when the universe had fewer heavy elements and might lack the material needed to form Earth-like worlds. If life does exist elsewhere in the galaxy, it's almost certainly microbial. Single-celled organisms dominated Earth for billions of years before complex life evolved. Intelligent, technologically advanced life may be even rarer. The conditions that led to human intelligence on Earth involved many chance events, and it's unclear how likely such pathways are elsewhere. Still, even if intelligent life is rare, microbial life might be common, hidden in the subsurface oceans of icy moons, in the atmospheres of gas giants, or on rocky planets orbiting distant stars. The search for extraterrestrial intelligence, or SETI, involves scanning the skies for signals that might indicate the presence of advanced civilizations. Radio telescopes listen for narrowband signals, or repeating patterns that could only be produced by technology. So far, no confirmed signals have been detected. The galaxy is vast, and if civilizations are rare, they might be separated by such enormous distances that communication is impractical. Or perhaps advanced civilizations are quiet, not broadcasting their presence, or they use technologies we haven't thought to look for. Even without direct evidence of extraterrestrial life, the Milky Way is filled with the building blocks of biology. Organic molecules, complex carbon-based compounds, have been detected in interstellar clouds, in comets, and on asteroids. These molecules include amino acids, the building blocks of proteins, and simple sugars, essential for the chemistry of life. The raw ingredients for life are widespread throughout the galaxy, mixed into the gas and dust from which new stars and planets form. It's possible that life arises wherever conditions allow, seeded by the organic rich material present in every stellar nursery. We are part of the galaxy, not separate from it. The atoms in our bodies were forged in stars, scattered into space by supernova, and eventually incorporated into the solar nebula that formed the sun and planets. We are, quite literally, made of stardust. The calcium in our bones, the iron in our blood, the oxygen we breathe. All of these elements were created in stellar furnaces and explosive deaths. In that sense, we're intimately connected to the galaxy and its history. Whether or not we ever find evidence of other life, the Milky Way is our home. It's the vast ecosystem that nurtured the sun and earth, that provided the elements necessary for life, that shaped the conditions in which we evolved. understanding the galaxy is, in a way, understanding ourselves and our origins. Conclusion. And so we've drifted through the Milky Way, from its hidden dark matter halo to its spiral arms ablaze with new stars, from the monster black hole at its heart to the ancient metal-poor stars in its outer halo. We've traced its collisions with smaller galaxies, witnessed the discovery of ripples and waves moving through its disk, and contemplated its future merger with Andromeda. We've marveled at the precision of Gaia's measurements and the stunning new views from radio telescopes. And we've considered our place in this vast system, a small world orbiting a modest star in a quiet corner of one spiral arm. The Milky Way is not a static backdrop. It's a dynamic, evolving structure, shaped by gravity, fed by gas from the intergalactic medium, stirred by mergers, and constantly recycling matter between stars and the interstellar medium. It has a history stretching back over 13 billion years, and it has a future that will see it merge with other galaxies, form countless new stars, and eventually, trillions of years hence, fade into darkness. But for now, tonight, as you drift towards sleep, know that you're part of this grand structure. The light from distant stars is reaching your eyes after traveling for thousands of years across the galaxy. The atoms in your body were once inside those stars, forged in nuclear furnaces and scattered by cosmic violence into the space between stars, only to be gathered again into clouds that formed the sun and earth. You are a piece of the galaxy, a momentary arrangement of stardust that has become aware of itself and its surroundings. The universe is vast, almost incomprehensibly so, but the Milky Way is our corner of it, our home on the largest scale. As you close your eyes and let sleep take you, imagine the galaxy turning slowly overhead, a great wheel of light in the darkness, billions of stars tracing their paths through space, clouds collapsing to birth new suns, ancient stars remembering the galaxy's youth, and somewhere in the Orion Spur, a small blue planet where thinking beings look up at the night sky and wonder. Before you go, if you've enjoyed this gentle journey through the cosmos, and these explorations help you wind down at the end of your day, please consider liking this video and subscribing to Sleepy Science Society. Your support helps these calm conversations about the universe reach others who might need a peaceful way to end their day. Thank you for joining me tonight. Rest well, dream of spirals and starlight, and remember that under the same vast sky, we're all adrift in the same cosmic current, carried along by the slow turning of the galaxy. Good night.